Welcome back. So today we're going to be sort of wrapping up this couple of weeks that we spent talking about spin before we move on to more complex Hilbert spaces, or shall I say, bigger Hilbert spaces. But before we do that, I want to sort of wrap up some of the last details about spin so that we can get all of our languages aligned with what the book is saying, and what I say, and what other people say, and try to get us all on the same page with some of the terminology that we've been using. And to do that, the first thing I'm going to do is I'm going to introduce, finally, the idea of the total spin vector as something of a quantum mechanical quantity. Now we know that there is this spin vector whose components are Sx, Sy, and Sz, the three different operators that give us measurements of the components of the spin operator. And we spent a lot of time thinking about how the three components of the spin operator have really a complicated relationship, right? We can know one of them, but we can't ever know more than one. And if we measure one, then we've destroyed all of the information that we have about the others. And so I've been able to, up till this point, measure one of the three components of the spin, and I know, based on how many beams come out of the Stern-Gerlach experiment, how many different possible measurements there are of that spin. Is there anything I can do with that to bring it back to the whole system, or bring it back to the idea of this spin vector? And I can do this, but I can't do it through the vector operator S, right? That thing we know we can't ever measure because it has three components that are fundamentally, not simultaneously measurable. However, if I take the dot product of the spin operator with itself, and now the notation here is just to make sure we're talking about the same thing, and there are a lot of S's flying around. So what we're going to write the spin squared operator as S with a vector sign, or your book it's bold, but S vector sign squared. Okay? And that feels like it's bad notation, but it really is shorthand for S vector dot S vector. Okay? And that is the square of the total spin vector, and it's of course a scalar operator. Not really, right? It's really an operator because each of the three components of S are matrices, but it's not a vector operator, okay? So it doesn't have I hats, j hats, or k hats associated with it, okay? And in this case, it will, when we give it a representation, it will be a matrix. But this S squared operator is special because when I do the components out, and you will do the components out, I find out that the S squared operator commutes with Sc. Right? So the commutator of S squared with Sc is equal to 0, which means that, if you remember from what we've been doing this last week, it means that you can simultaneously know what the value of Sz is and what the value of S squared is. Okay? And that means that if I have a state of Sz, I can throw that state into the S squared operator, and now I'm not able to actually build this thing, okay? So this is a more mathematical concept than that, but I'm able to construct it, and I'm guaranteed that the eigenvalues, the eigenvectors of Sz will also be eigenvectors of S squared. Now, this is an important point, and one that I got wrong once and never lived it down. Okay, so I'm hoping that you never get to this point where you'll forget this like I did that one time. It would be great if the eigenvalues of the S squared operator were the spin of the system squared, but they're not. They're an integer S times S plus 1. Okay, and so if I apply the S squared operator to some system, I'm going to get out an integer that's actually the product of some integer S with the combination S plus 1. And I shouldn't have said integer, right? Because S, we already know, we've talked about spin 1/2 systems where S is a half integer. So forget I said integer this whole time. It's a number times that number plus 1. Okay? And in fact, it's the value of that eigenvalue, right? It's the value of that thing that actually leads us to calling these spin 1/2, spin 2, spin 3s, spin 17 half systems. But just remember that eigenvalue is not the total spin squared, or is not the spin quantum number squared, it is s times s plus 1. And as I said, the consequences of this are really cool. First is that I know that the commutator of s squared with sz is 0, which means that I can know both the total spin and the z component of the spin vector at the same time. Well, turns out I can commute s squared with sx and s squared with sy as well, right? Which is awesome. It turns out that no matter what I do to this state, it's always going to commute with the s squared operator. And there's a property of the s squared operator, I hate to give it away, maybe I'll give it away. It's proportional to the identity matrix. Maybe that's a hint for your problem set. This property of the s squared operator means that it'll commute with any of the spin operators. And so if you have states of sx, sy, or sz, you can apply the s squared operator and get out what the total value of the spin is. And that's pretty darn convenient. And it does not imply, and this is a question about commutivity, right? Sz commutes with s squared, and sx commutes with s squared, but this does not mean that sz commutes with sx, right? And so commute here has an extra meaning that maybe isn't totally consistent with our old-fashioned way of thinking about commuting. And so now, what does this scalar value s mean? What does this eigenvalue of the s squared operator means? Well, we use that eigenvalue to identify what we call the spin of the system, or the total spin of the system. And this is the number that we've been using when we talk about a spin 1/2 system or a spin 1 system. So if I calculate this eigenvalue, if I measure this eigenvalue, I know that a system that has spin s is going to have 2s plus 1 possible measurements of any component of the spin vector. So if we do this quickly for a spin 1/2 system, 2 times 1/2 is 1, plus 1 is 2, and indeed for a spin 1/2 system there are 2 possible measurements of any component of s. And in addition to that, right, s is going to be just a number, right? It's a number associated with that eigenvalue. And oh man, that hits me that I made a mistake here. I'm sorry. I'm going to go back because this is a really important one. There is an h bar squared in front of this measurement. I can't believe I made that mistake. Okay, at least I corrected it. Okay, there's an h bar squared there. And I knew that because s times h bar, right? So s is the quantum number, but s times h bar is the measurement. That s times h bar is the maximum possible measurement of any component of the spin, right? So again, let's go back to our intuition from the spin 1/2 system. If s equals 1/2, then 2s plus 1 is 2 possible measurements. And the biggest possible measurement is going to be s times h bar, which is 1/2 h bar, and indeed, that is the largest possible measurement that I can get from a spin 1/2 system through a Stern-Galactic experiment. And by possible measurement, I mean, of course, any of the particular components. And so now I know that I can think about the total spin, right? I have sort of this idea of some way of talking about the magnitude of the spin vector. But I want us to really connect this, right? So the spin is associated with the magnetic dipole moment of my particles, right? This is back to day 1 of this class, that when we're measuring spin, we're really measuring the magnetic dipole moment of these particles. And we've discussed that magnetic dipole moment doesn't literally come from the particle moving, right? That we showed that actually, some of you showed that in another class, that it's not possible, for example, to talk about an electron actually spinning to generate this magnetic dipole moment. And therefore, the angular momentum associated with this magnetic dipole moment is not from the physical rotation of the particle, but is an inherent property of the particle. Okay? So our particles that have spin have intrinsic angular momentum that generates this magnetic dipole moment. That is the thing that we call spin. right? And that's our picture then that we sometimes see in these atomic physics talks where you have a ball, right, and the spin vectors coming out of it. And again, you don't want to think about it actually spinning, but you do want to think about having some intrinsic angular momentum, therefore intrinsic magnetic dipole moment associated with this fundamental particle. And since it's a vector, right, and since we're talking about angular momentum and we're talking about what happens when things rotate, right? That's what angular momentum is all about. If I choose a direction, angular momentum is a rotation about that direction. Then the components of the spin operators then have to have all of the mathematical baggage that comes along with worrying about rotations in three-dimensional space, right? That the x component of the spin really is angular momentum about the x-axis. The z component is angular momentum about the z-axis. And therefore, the relationship between my devices that measure these components have to so-called obey the algebra associated with the set or the group of three-dimensional rotations. Now, I don't, for those of you who are either math double majors or have taken group theory or abstract algebra, maybe this is something, maybe this is a part of the recording that you're going to watch a couple of times. But for those of you who want me to get to the point, like, why are you telling me this? Well, I want you to notice that the relationship defined by the commutator of my spin operators, that is the commutator of Sx with Sy being proportional to Sz, should exactly remind you of the relationship between the unit vectors when I take the cross product. That is, I hat cross j hat is k hat, right? X cross y is z. And all of that comes down to the fact that I'm not able to commute three-dimensional rotations. And this is something that I always have struggled with. So if you take a book, right, and you rotate it, and I always have to do this, right, rotate it around the x-axis and then rotate it around the y-axis, you get something different than if you rotate it around the y-axis and then rotated it around the x-axis. Okay? And so the reason that we have these matrices, or the reason that we establish the relationship between the different components of the spin matrix, the different operators that are the components of the spin vector, I'm sorry, not spin matrix, those matrices obey the same algebra as our unit vectors do, right? And all of this comes down to the fact that I'm really talking about rotations in three-dimensional space. And every time I have rotations in three-dimensional space, I'm representing this group. And this group is called SU2, the special unitary group. Blah, blah, blah. Anyway, the point is that this group is going to be the thing that we identify with angular momentum because it inherently talks about the rotations in three-dimensional space. And therefore, you'll often hear me talk about our spin matrices, or your book talk about spin matrices, as a representation of this group. And so if I have a spin system of spin S, I know that there are going to be two S plus 1 measurements, let me call that number n, and therefore my three operators, Sx, Sy, and Sc, are always going to be three matrices that obey the commutation relations that I showed you on the last slide. And we call that an n-dimensional representation of SU2. Okay, that's the big fancy word that we hear when we talk about, when we actually put the group language into this problem. Okay, and so when I say the four-dimensional representation of SU2, well, that means there are four measurements of any particular component, which means that I'm talking about a spin 3/2 particle. Okay. Luckily, I'm never going to ask you to come up with these matrices in this class, right? From now on, when I say look up a spin 7/2 particle, you can just look up those matrices because thank goodness mathematicians for a long time before quantum mechanics were able to study the SU2 group. And by studying the SU2 group, they were able to come up with matrices that already had that algebra with them, right? And so many of you have asked me over the course of the last couple of weeks, like, why does the Sy operator look like this? Why does the Sx operator look like this? Well, it turns out, especially for 2x2 matrices, there's a unique way to write down those three those three matrices. For higher dimensions, it turns out, if I remember, it's not exactly true, but we have a set of representations of SU2 for all of the dimensions that we care about, and therefore we're just going to look them up, right? And that we may verify that they have the right commutation relation, and we may calculate the eigenstates and eigenvalues associated with those to make sure that they confirmed with what we see in our measurements. But we really do have to be thankful for the fact that somebody else did most of the hard work in generating representations of SU2 of almost any dimension. Okay, so here are our take-home messages. One, the first thing we talked about was that we now can talk about total spin. And the only way to measure that, or to get an eigenvalue out of it, is to use the s squared operator, which is s dot s. And that s dot s operator is the total spin. And that s squared operator commutes with sx, sy, and sz, which is outstanding. And of course, the eigenvalue of that s squared operator has an h bar squared times s plus 1, not just s squared, right? It's s times s plus 1. And then a system with spin s has n equals 2s plus 1 possible measurements of xy, x, and sc, which, as we just said, means that the operators sx, sy, and sc are n-dimensional representations of SU2. Okay? Good luck. See you next time.